Now we're gonna do section 7.2, which is about the sum and the difference formulas. And these are really one of the most basic ones, because once you have these formulas, then we can use them to derive the rest. Okay, so these are very important, the sum and difference formulas. So let me start here with the fundamental question that we're trying to ask. So the kind of question that we want to solve here is the following. First, we're going to focus on cosine. And once we do cosine, then you will see how easily we're going to get the formulas for sine. And as you know, once you have sine and cosine, we can translate these, to tangent and then the others. So sine and cosines are the basic ones. Okay, so here is one of the questions that we want to answer. Imagine that you want to calculate cosine of 75 degrees. Okay, we would like to calculate this without using a calculator. Is it possible to do this? To do this exactly? Well, one way to approach this is, well, you could say that cosine of 75 can be written as 30 degrees plus 45 degrees. And we know how to deal with 30 degrees independently, and we know how to deal with 45 degrees independently, because these are the special angles, right? So a natural question is, can we express this somehow as as an expression that involves functions of only 30 and 45 degrees? So that's something that we may wonder. So can we express this as an expression involving only functions of 30 and 45, only functions of 30 degrees and 45 degrees. Because if we do that, then we'll be able to calculate these values, because it's at the special angles, and then we will be able to know exactly what the cosine of 75 is, for example. And in a similar way, so similarly, instead of saying that 75 is 30 plus 45, you could say, well, 75, we can think of it as being the sine of 15. Cosine of 75 is the same as the sine of 15. Remember, I'm using the cofunction theorem that says that the 75 and 15, these are complementary angles. When you add them, you get 90 degrees. So the cosine of one is the sine of the other, as you all know. Then you could say, well, 15 degrees, we could write it as 45 minus 30. So again, the question remains, do we write the sine of 45 minus 30 degrees as an expression that involves only 30 and 45? So same sort of question. So this is what we're trying to explore right now. Do you understand what we want to do? Okay, so let's see what we can do about it. So let us try to, generalize this type of question. I mean, I just picked 75, but it doesn't have to be 75. So in general, the question that we try to answer is, if you have the cosine of the sum of two angles, let's call them alpha beta and beta, or cosine of the difference of two angles, let's call them alpha minus beta, can we say what is this equal to? So we would like to write this as an expression. So we want to find an expression involving trigonometric functions of alpha and beta only. Okay, so we would like to somehow do a kind of splitting of an expression like this. And then, of course, similarly for the sine function, but like I said, we're going to treat the sine later. So this concerns now in figuring out cosine of the sum of two angles or cosine of the difference of two angles. So first, I want to give an idea, which is the fact that if we know, for example, the cosine of the difference, then we will get for free the cosine of the sum. So let me write that down. So remark, if we know, so assume that we already know what to do with cosine of alpha minus beta. So assume that we have a formula for cosine of alpha minus beta. If we can find a formula for this, then we can actually deal with the sum pretty easily, because cosine of alpha plus beta, we can rewrite this as cosine of alpha minus beta. Okay, and we have done these tricks before, so you can always write, a positive number, you can write it as minus minus. And the point is that if you already have a formula for alpha minus beta, so the difference of two angles, you can now use it in this form. And then once you use the formula, so here you use formula. And yes, you're going to have expressions with negative beta, but then you can use the even odd identities to get rid of that negative in front of the beta. So use the formula and then use even odd identities. So the moral of the story is that we can actually narrow down our focus into what to do if you have cosine of alpha minus beta. Once we get this, then the rest will follow easily. Do you understand why cosine of alpha minus beta will be our focus now? Yes or no? More or less. Okay. What is it not clear to you in this remark, Maria? Do you know what I mean when I say even odd identities? Okay. So all I'm saying here is that if we already know a formula for cosine of a difference of two angles, then you will get for free the formula for the cosine of the sum. Because you can play this trick. You can write the sum as minus minus, and then you use the formula for the minus, and then one of the angles will be negative beta, but then you can get rid of the negative by using even odd identities. That's what they are there for, to get rid of the negative. Okay? And so we're gonna restrict our attention. Remember, we're interested in two formulas, but what this remark is telling you is, if you know one formula, the one for the difference, then you will get for free the other one. So we're going to discuss that, okay? So, we're going to discuss, so let's discuss what happens with cosine of alpha minus beta. Again, I could just give you the formula, but there is no point in doing that. I mean, you can just read that in the book on your own. The point is that, it's kind of interesting to see how this formula comes up. So you can see the geometry that's happening behind the scenes, okay? And if you ever forget the formula, hopefully you can do what we are about to do and then somehow recover this formula. Because this formula is really the base for all the other identities that we're going to write down the line today. Okay, so let us try to find an expression for cosine of alpha minus beta. So to do this, let us assume, without loss of generality, we can assume that beta is less than alpha. I'm doing this just because I want alpha minus beta to be positive. If that's not the case, if beta is bigger than alpha, that's okay. Cosine is an even function, so that means that you can factor out a negative, and this actually is effectively the same thing as cosine of beta minus alpha. Okay, and just to show you this, alpha minus beta, you can write it as minus beta minus alpha. So if you do cosine, it's like doing cosine of this. But remember, cosine is an even function, so it kills the minus. So cosine of alpha minus beta is the same as cosine of beta minus alpha, okay? So if beta happens to be bigger than alpha, just flip them and then relabel them and call alpha the bigger angle and beta the smaller angle, okay? So this is just to have a nicer picture. So assume then that beta is positive and less than alpha. Okay, because otherwise if beta is negative, then you don't have a minus, you have a plus in there, right? So I want to have a minus inside. Okay, so in this case, then we can have a picture. So let's see, I'm gonna draw a typical picture. Let's say maybe beta is in quadrant 1, and then let's say alpha is in quadrant 2. Again, it doesn't matter. It could be they could be in other quadrants as long as alpha is bigger than beta. All right, I'm just gonna draw the picture with beta in quadrant 1 and alpha in quadrant 2. So of course, we're gonna have our unit circle. That's x, that's y. So let's do here our unit circle. So 1, 1, -1, -1. And so let's say that beta is somewhere in here. So this is the angle beta. And as you know, there is a point corresponding to it. Let's call it P. So this is our angle beta right here. That's the terminal side. And then alpha, let's put the terminal side of alpha somewhere in quadrant 2. Alpha is bigger than beta, so let's say it's in quadrant 2, something like this. So all of this is alpha, okay? All right, so then first I want you to realize what this angle is. Can anybody tell me what is this angle that I'm doing in green? This green angle, how can we calculate that? That would be the difference of the two angles, right? So it would be alpha minus beta. Do you guys see this? That green angle is alpha minus beta. Okay, good. Now alpha also gives you a point on the unit circle. Let's call that point, let's call it Q. And then we're gonna pay attention to the following. We're gonna pay attention to this triangle that is formed here. Okay, so there is a triangle that's being formed. And I mean, the picture suggests that P and Q are at the same level, but it doesn't have to be. It's just because of the way I draw it, okay? Let's get the 2 points, P and Q, and then just draw the line segment that joins P and Q. I'm gonna call that side, let's call it D, the length of that side, okay? It's gonna be D. All right, so we have this picture. Now what I'm gonna do is the following. Let us take this picture and let us rotate this picture clockwise by the angle beta. In other words, I'm going to take this picture and I'm going to rotate clockwise by beta. So what does that mean? It means that the terminal side of beta, the red side, is going to then coincide with the x-axis because I'm rotating like that. So it's gonna coincide with the x-axis. And then the blue side, it could land on quadrant 1 now. All right. So what I'm gonna do is rotate that. You might taking that picture in mind that that circle is like a wheel, and you just turn it clockwise by an angle beta. Okay, just turn the circle around with everything that it has inside. So because we're doing a rotation in particular, notice that that means that we are keeping all the shapes the way they are. In other words, the triangle that we get is going to be the same triangle. It's just that it will be in a different position. So the area is preserved, perimeter, length, everything is preserved here, okay? So we take our circle and we rotated that picture. So we get another unit circle here, but then we get something different, right? So this time we have that what was the green, the red side over there becomes part of the x-axis. So now we get here a new point, let's call it P prime. That's the one corresponding to P when you do the rotation. And then the blue side will go somewhere in here. When I get a point here, let's call it Q prime. That's the one corresponding to, the blue side that we have over there. Q prime corresponds to Q. Now I want to ask you a question. Can anybody tell me what is this angle that we have here? What would be this green angle? Do you think this angle is going to be the same or different than the one that we had earlier? It's going to be the same. Very good. This still be alpha minus beta, okay? Because all we did was rotate the picture. That's all. We did not change anything else. And so in particular, what do you think is going to happen to this side? What is this side, this segment Q prime, P prime? What can we say about it? It's going to be the same, right? So that's going to be D as well. Very good. Okay, so we get here another triangle. I'm going to shade it with the same color because the point is that the two triangles that we have are the same, right? These triangles are going to be equal to each other. All I did was I rotated. Okay, so now let us look at these pictures a little bit more deeper and let us write down the coordinates of each of the points that we have. Let's see, the point P. Can anybody tell me what are the coordinates of P? what are the coordinates of P? Remember, this is a point on the unit circle. What do we know about points on the unit circle? How do we write the coordinates of a point of a unit circle? They define an angle, yes. So what do we know about the x value of the point? It's going to be the cosine of the angle. And what do we know about the y value of the point? It's going to be the sine of the angle. So remember, by definition, the points on the unit circle, they have the form cosine, comma, sine, right? Do you remember this? Okay, good. And then similarly, what can we say about Q? What are the coordinates of Q? Q has coordinates cosine of alpha, comma, sine of alpha. So remember, the idea that we want is, notice how we brought alpha minus beta into the picture. Notice how we have now stuff that have cosine of alpha, sine of alpha, cosine of beta, sine of beta. And I wrote here sine of y, not sure why. And that's what we want. Remember, we want to bring these quantities into the picture because what was our goal? To write cosine of alpha minus beta as an expression involving only alphas and betas, trigonometric functions of alpha and beta. Okay, so we are in the process of doing this. All right, so that completes our picture on the left. Now let's complete the picture on the right. What's the coordinate of P prime? Who can tell me the coordinates of P prime? Come on, that's the easier one to get. Look at the picture. You can do better than that. Look where I draw P prime. What's the x value? It's on the x-axis and we are on the unit circle. So what's the x value of P prime? No. Look at the picture. It's a very easy question. Look at the picture. Where is P prime? 1. So what's the coordinate? What's the coordinate of P prime? 1,0. Very good. So P prime now becomes 1,0. That's the reason why we did the rotation. I mean, we rotate it so that we can get, something nice. So when you do the rotation by beta, that makes the terminal side of beta coincide with the x-axis. So now we get our P turns into P prime, but now the coordinates are nice. It's 1,0. And then what are the coordinates of Q prime? So Q prime now, the angle is alpha minus beta, right? So this is going to be cosine of alpha minus beta, comma, sine of alpha minus beta. Now we are in business because we are bringing the cosine into the picture of alpha minus beta. Okay, notice that here is cosine of alpha minus beta, and that's what we are interested in. Of course, there is other stuff happening, but hopefully those things will fade away. So let's see what happens with those. Okay, questions? Do you understand how we build this picture? Because, the key, everything here, the key would be this picture. Everybody okay with this? Okay, now let's do some algebra. This is the geometry, now let's do some algebra. Okay, what do these two pictures have in common? So we have the angle alpha minus beta, yes? What else do the two pictures have in common? Anybody? The length of the sides. So in particular, what side do you think would be relevant for us? So we have alpha minus beta, then we have the side D, right? So we have D, which is the same for both. So the segment QP, that's equal to D, the length of that segment on the first triangle. In the second triangle, the segment Q prime P prime equals to D as well. So we have this quantity D that actually is a connecting point between the two, right? So by looking at the first triangle, we have that D can be thought of as the length of the segment QP. But then if you look at the second triangle, we can think of D as the length of the segment Q prime, P prime. Do you understand this? All right, but how do you find the length of a segment? You just use the distance formula, right? Because when you have a segment, that means that you have two endpoints. And if you know the coordinates of the endpoints, then you can use the distance formula. So what does that mean? What's the length of QP? So the length of QP is going to be square root of, then you need to subtract the x's, and then square it, and then subtract the y's. So this is cosine of alpha minus cosine of beta squared plus sine of alpha minus sine of beta squared. Everybody okay with this? Do you understand this? For the segment QP? Yeah, I'm trying to do it slowly so I don't lose anybody. But are you following what's going on? All right, so now this is the same thing as D, but then once again, now we can do the same thing, but on the other side, we can look at the length of the distance Q prime, P prime, okay? So once again, we use the distance formula, all right? So this will be square root of difference of the x's, cosine of alpha minus beta minus 1 square plus difference of the y's. So in this case, that's just sine squared, right? Because we have sine minus 0. All right, let me just specify that. So sine minus 0, sine of alpha minus beta minus 0, and then squared. Okay, so we have these two expressions, these two big radicals, and they are actually equal to each other. So the geometry is over. So I've noticed that the equality of these two radicals is justified by the picture, by the construction that we made. All right. So now that we have this construction, now we can just do algebra on this. Now I'm just gonna do algebra and clean up this, and hopefully something nice will come out of this. Okay. All right. So let's begin. So of course, remember, what is our goal? Our goal is to say something about this guy. Cosine of alpha minus beta. That's what we want, okay? All right, so now I'm gonna start cleaning stuff. So for example, I'm gonna square both sides. Okay, Ramses, don't worry. Just make sure that, just watch the beginning of the video later so that you can see how we arrived to this expression, okay? So you understand the construction in the pictures and so on. Okay, so I'm gonna square both sides. So we get to get rid of the radicals. So we get cosine of alpha minus cosine of beta squared plus sine of alpha minus sine of beta squared, and that's going to be equal to cosine of alpha minus beta minus 1 squared plus, okay, so sine minus 0, that's just sine, so that would be sine squared of alpha minus beta. Okay, so now what I'm going to do is I'm just going to expand the squares on both sides, all right? So here we get cosine squared minus 2 cosine of alpha cosine of beta plus cosine squared of beta, and then plus, and then I expand the other square. That's sine squared of alpha minus 2 sine of alpha sine of beta plus sine squared of beta, and that's going to be equal to, I'm going to do the same thing on the right hand side. So cosine squared, then minus 2 cosine, because there is a 1 in there, and then plus 1, and then remember we have a plus sine squared of alpha minus beta. Okay, questions on what we have here so far? questions here? Okay, now a lot of nice things starts to happen. So for example, notice that on the left hand side we have cosine square of alpha plus sine square of alpha. What do you know about that? What's cosine square of alpha plus sine square of alpha? What is that equal to? It's equal to 1. Very good. Now notice that we also have cosine square of beta plus sine square of beta. What is that equal to? So let me maybe use another color for that. So we have this with this. What is this equal to? That's equal to 1 as well. Very good. And now with the terms that are left, notice that we can take out, let's see, we can factor out a -2. So I will factor out a -2, and then we get cosine of alpha, cosine of beta, plus sine of alpha, sine of beta. So this is what we obtain on the left hand side. Now on the right hand side, we can do something similar. Notice that we have a cosine square of alpha minus beta plus sine square of alpha minus beta. The angles are the same. So what do we know about that? That's equal to 1 as well. And notice that these are lucky day, because now on the left hand side, what we have is actually what we're looking for, right? We have cosine of alpha minus beta. So now we just solve for it, okay? So notice that in this case, this one cancel with this one over here cancel with this one over here. So we are left with -2 times cosine of alpha, cosine of beta, plus sine alpha, sine beta. And this is going to be equal to -2 cosine of alpha minus beta. So now we just divide by -2. So this -2 cancel with this one. And then finally, we obtain, so we have the cosine of alpha minus beta. What is this equal to? This is cosine of alpha, cosine of beta, plus sine of alpha times sine of beta. So the way I like to remember this is that this is cosine of alpha minus beta is cos plus sine. Okay? So remember the sign changes from negative to positive, and then it's just cos plus sine. All right, so this is our first formula, our first identity of cosine of the difference of two angles. Questions? Okay, perfect. Now, as promised, remember that what the observation that we made here was that once we knew the formula for cosine of alpha minus beta, we should be able to get for free the formula of cosine of alpha plus beta. So let us do that now. Since we already have a formula, remember this is what we wanted. We wanted to write cosine of alpha minus beta as some expression that involves only cosines of alpha, functions of alpha and functions of beta. And that's exactly what we have here, okay? So now, to figure out the other one, we can do it very easily. So if you want to find cosine of alpha plus beta, well, we do the trick. We write this as cosine of alpha minus beta. Now let's use the formula that we have above. So this is cos plus sine. Okay, but now we're gonna use the even odd identities. So what do we have for the even odd identities? Remember, cosine is an even function, so it gets rid of the minus. So cosine of negative beta is just cosine of beta. And now sine is an odd function, so you can take the minus out. So the minus of negative beta comes out, turning the plus into a negative. And then we get our formula for cosine of alpha plus beta. So cosine of alpha plus beta is the same as before. It's just that instead of a plus, we have a minus in the formula. Cos cos minus sine sine. Okay, questions about the sum formulas for cosine? Yes, Maria? What's your question? If you're talking, I cannot hear you. You need to activate your mic. No, so remember, what do you know about cosine? Cosine is an even function. What does being even mean? Even means that you get rid of the negatives. Remember, even means that f of negative x equals f of x. That's what it means to be even. Okay? Odd means, so this is even, and then odd means that f of negative x equals minus f of x. You take the negative out. That's what it means to be odd. So cosine is even and sine is odd. So that's why the cosine got rid of the negative, but the sine, it take it out. So that's why you have a minus instead of a plus. Okay, perfect. Okay, so again, these formulas are important, so it's important to know them. They will help you deal with several situations. Okay, so like I said, then how the sine get the negative again? Well, look at it. It's right there. We did a trick. The plus beta, we had a plus beta here. What do? We wrote it as minus minus. You see that? And then, since now we have why did we do that? Because we wanted to have a subtraction. We wanted to have a difference of two angles, so we could use the formula that we have from above. Okay? So that's why then we have a negative beta here instead. But then we use even odd identity to clear up the negative inside. We don't want that negative to be inside, so we take it out. Sometimes survives, like in the sine case. Sometimes it doesn't survive, like in the cosine case. But the negative is just gone because cosine is even. All right, so these are important properties. Okay, so you need to know these identities. And again, one quick way of remembering this is that the cosine will give you cos cos sine sine. And remember, you change the sign. So if it was minus, it becomes plus. If it was plus, then you get minus. Okay. All right, so let us see some examples of how we can use this. So for example, let's say that we wanted to calculate, as before, cosine of 75 degrees without using a calculator. Well, if you want to exactly find this, well, you should realize that 75 can be written as 45 plus 30. And why are we writing as this and not 70 plus 5, for example? Well, because 45 and 30 are angles that we recognize, that we know the values, okay? Now we can use our formula. So this is going to be cos minus, it changes the sign, remember, sine sine. And so now we can use what we know. So cosine of 45, that's square root of 2 over 2. Cosine of 30, that's square root of 3 over 2, minus sine of 45, square root of 2 over 2, sine of 30, that's 1/2. So we have denominators of 4, so we can nicely combine these and get a square root of 6 minus square root of 2 over 4. So this allows now to calculate other angles without the need of a calculator. Among other benefits that we're going to see, but this is a nice little application. You can now expand your arsenal of values that you can calculate without a calculator. Okay, questions? Okay, good. So let's see, what else can we do? Let's do another example. Let's do one with radians. So let's say that you want to find cosine of pi over 12. All right. So notice that pi over 12 is the same thing as 15 degrees. Okay. So if you do 180 divided by 12, that's 15. So that means that you can write 15 as 45 minus 30. And in this case, pi over 12, we're working with radians. You have to figure out how you can split this. It turns out you can write it as pi over 4 minus pi over 6. Again, the easier way to probably see this is think of pi over 12 as 15 degrees, and then you can see there the convention because it's really, when we look at degrees, it's kind of intuitive because they're closer to the numbers that we're used to. So as 30 degrees, so 30, that's 15 degrees. 15 can be written as 45 minus 30, but then 45 is pi over 4 and 30 is pi over 6. Okay, so that's what I would recommend. If you want to do it at the radian level, then you need to be a little bit more creative. How to see that? Yeah, you have to be more creative. Like, how can you write pi as a difference of two multiples of two numbers that can be, that are factors of 12? That's basically what you need. And then maybe if you think about it a little bit, you realize that you can write pi as 3 pi minus 2 pi. Okay. And then when you split pi over 12, then that would be pi over 12 would be this over 12. And when you split it as a fraction, then you would get 3 pi over 12 minus 2 pi over 12. This one giving you pi over 4, and this one giving you pi over 6. Okay? But again, this you have to think more. I think it's easier to just think of the angle in degrees, write in degrees, find the splitting, and then you go back to radians. Because remember, we are working with radians. But it doesn't mean that we ignore degrees. Okay, anyways, once we realize that pi over 12 can be written as this difference, then we use the formula. So this is cos, and then plus sin. All right? And so cosine of pi over 4, that's square root of 2 over 2. Cosine of pi over 6, that's square root of 3 over 2. And then sine of pi over 4, that's square root of 2 over 2. And then sine of pi over 6, that's 1/2. So what do we get here? So we have square root of 6 plus square root of 2 over 4. That's cosine of 15 degrees, or pi over 12. Okay, questions? Questions on number 2? Okay, we now know what's the cosine of the difference and the sum of two angles. So a natural question is, how about the sine? Can we figure out what is the sine of the difference of two angles and the sine of the sum of two angles? And for that matter, what will be the tangent and so on? So we have identities for all of that. So let us try to understand how to obtain those. So far, I want you to see that alpha plus beta, cosine of alpha plus beta, was obtained from the difference. So far, this one is a key. Okay. Once you know cosine of alpha minus beta, you can work your way through and come up with the others. That's the point. So let's see if we can do the same thing for the sine. Okay, so let's talk about the cofunction identities, and this is something that you already know from before. And the point is that we're going to exploit this to actually obtain a result for the formulas for sum and difference of sine. Okay. Because remember, cofunction identities, this is just a way of turning cosines into sine. You just have to change the angle for its complementary, at least in the acute case. So let me remind you of this. So recall. So if theta is an angle that's between 0 and pi over 2, meaning if it is an acute angle, it's in quadrant 1, then that means that we can fit theta into a right triangle, right? So say theta is here, and therefore we put in a right triangle, so there is a corresponding angle that's called alpha, and the property that we know is that both theta and alpha are complementary. In other words, they are up to 90 degrees. They are complementary. And we know also, the relationship between complementary angles is that the sine of one is the cosine of the other one. So cofunction of complementary angles are the same. So what do we know about sine of theta and what do we know about cosine of theta? Well, the sine of theta is the same thing as cosine of alpha, and the cosine of alpha is the same thing as cosine of theta is the same thing as sine of alpha. All right, and again, this is something that we discussed earlier. Are there any questions on this so far? Okay, now I want you to realize that in this case, in the complementary case, right, alpha is complementary to theta. So what does that mean? It actually means that we can write alpha as pi over 2 minus theta, right? So in this case in particular, this alpha is the same thing as saying pi over 2 minus theta. You remember they are complementary, meaning that their sum is 90 degrees. So complementary, so I alpha plus theta is pi over 2. Okay, they fit inside a right triangle. And then similarly, we see that sine of alpha is the same thing as sine of pi over 2 minus theta. Okay, so then the question is, okay, so we have this relationship among acute angles. So if an angle is acute, that means that you can write the sine as cosine of pi over 2 minus the angle. And the cosine, we can write it as sine of pi over 2 minus the angle. Now the question is this always true? Is this true for any angle, not necessarily an acute angle? What if theta is not acute? Okay, so that's a natural question to ask, and then let us try to see if that's the case or not. Let us take a look at cosine of pi over 2 minus theta. But this time, I'm gonna make this without the assumption that theta is acute. And let's say here for any angle theta. Okay, it's just theta is any angle, and let's look at the expression cosine of pi over 2 minus theta. We can understand this further because we know we have a formula for this now. What is this? Using the formula we just discussed, this would be cos cos plus sine sine. Okay, now what do you know about cosine of pi over 2? What's cosine of pi over 2? I'm asking you a simple question. What is cosine of pi over 2? Do you understand the question that I'm asking you? Okay, good, Alan. So Maria, cosine of pi over 2 is 0. Remember, think about the unit circle. Think about the unit circle. Very good, Isabella. So think about the unit circle. Pi over 2 corresponds to the point 0, 1. Cosine gives you the x value of the point. Okay? The x value corresponding to pi over 2 is 0. That's 0, 1. So in a similar way, what will be sine of pi over 2? Sine of pi over 2 is equal to 1. Very good. So what do we get here? So we're going to have 0. So 0 times cosine, that's just 0. So 0 plus 1 times the sine function. So now this time we remove the restriction of theta being acute, and we still obtain the fact that cosine of pi over 2 minus theta actually equals sine. And notice that this is true for any angle theta now. For any angle theta. It doesn't have to be an acute angle. Okay? So that relationship that we observe for complementary angles, so when theta is acute, the observation that we made when theta was acute, the sine of theta is cosine of pi over 2 minus theta, actually extends to any angle. Any questions? Questions on this? All right. Well, the point is that the second relationship that we have also holds. Okay. Cosine of theta is also the same as sine of pi over 2 minus theta, and this is true for any angle. So these are called the co-function identities. Okay. So we just proved one. The proof of the other one, we first need to know what sine of pi over 2 minus theta is, which we're about to do. Okay. So theorem. But as you can imagine, it goes in a similar way. So these are called the co-function identities. And this allows you to, having an angle, if you don't like to have sine, you can turn into a cosine. And if you don't want to have cosine, you can turn into a sine by using this identity. Okay? So for any angle, doesn't have to be acute anymore. The point is that these two that we have for acute angles is also true for any angle. Okay? So for any angle theta, we have, so number one, that if you do, okay, if you do cosine, I like to write it the other way. So if you look sine of theta, that's the same thing as cosine of pi over 2 minus theta. And then also, let's say you don't like to have cosine. If you have cosine of theta, you can rewrite it as sine of pi over 2 minus theta. Okay, these are the co-function identities. All right, so why am I bringing this up now? Well, because they will help us to find the sum and difference formulas of sine. So as an application, we're gonna use this to find the sum and difference formulas of sine. Okay, so in other words, what I mean by this is what would be sine of alpha plus beta, what is this equal to, and also what is sine of alpha minus beta. Okay, just like before, we're just gonna focus ourselves on figuring out what this is, because once you know sine of alpha minus beta, we can play the trick to come up with sine of alpha plus beta, right? And the trick is the same one that we use in the cosine case. We use the formula and then use the even odd identities. All right, so let's see, how can we use this in a clever way? Okay, so let's take a look at sine of alpha minus beta. Then, of course, I want to somehow use the fact that we already know how to deal with cosine. Okay, so if we use the co-function identity that we have above, that says that sine can be written in terms of a cosine, we can write this as cosine of pi over 2 minus alpha minus beta. Okay, so this is using the co-function identity. So that's co-function identity number one. Everybody okay with this so far? Okay, now I'm gonna play with this expression a little bit. So I'm going to actually collect terms differently. I'm gonna write this as pi over 2 minus alpha plus beta. So all I did was distribute the minus and then put the first two terms together, okay? And now, it should not come as a surprise, we're gonna use the formula that we already discussed about cosine. So we have that this would be cos, so cosine of the first angle times the cosine of the second angle, then minus, because we had a plus that turns into a minus, and then sine, the sine of the first angle times the sine of the second angle. Everybody okay with this? All right, so now let's use cofunctions identity again. What do we know about cosine of pi over 2 minus alpha? So using identity number 1, cosine of pi over 2 minus an angle, that's just sine of the angle, right? So this becomes sine of alpha, and then times cosine of beta, minus, using cofunction identity, what's sine of pi over 2 minus an angle? That's going to be cosine of the angle. So that would be cosine of alpha, and then times sine of beta. And here we go. So here is a formula for sine of alpha minus beta. Okay, so it's sine cos, cos sine, right? So remember, for cosine we had cos cos, sine sine. For sine we have sine cos, cos sine. And notice that in this case it respects the operation. If you have a minus, you still get a minus. And of course, if we, in the case of the plus, you will see we're going to get a plus. Cosine flips the operation, the sine keeps the operation. Questions about this first identity? What happened to the pi over 2? We use the cofunction identities. You see the cofunction identity that says that if you have sine of pi over 2 minus theta, that's the same thing as saying cosine of theta. Do you see that? Identity number 2. That's what happened here. So this guy became cosine of alpha, because that's sine of pi over 2 minus alpha, so that's just cosine of alpha. And similarly, if you have cosine of pi over 2 minus alpha, that becomes sine of alpha. All right, good. So that's the formula for the difference. Now, since we know the difference, we can go ahead and use the trick to come up with the formula for the sum. So if you want to know what sine of alpha plus beta, well, we just play the trick. This is sine of alpha minus beta. Now let's use the formula that we just figured out. So it's sine cos minus cos sine. But now remember, cosine is even and sine is odd. So in the first one, the cosine of negative beta, that's just cosine of beta. And then the sine of negative beta, the minus survive, we take it out, turning that negative into a plus, and we get cosine of alpha, sine of beta. So we have our other identity that says that sine of alpha plus beta is sine of alpha cosine of beta plus cosine of alpha sine of beta. Sine cos plus cosine. All right. Questions on how we obtain the sum and different formulas for sine? Okay, good. And again, you can see, applications are, similar to the ones that that we did before for cosine. So instead of using examples like those, let us quickly now, as a main application, we can actually come up with the formula for tangent. Since we now know everything about sine and cosine, we can say something about tangent. So corollary of these formulas, so direct consequence is the following. Corollary, we can say something about tangent, right? So let's figure out what is tangent of alpha plus beta. Okay, so again, if we want to come up with a formula for tangent of the sum of two angles, what can we do? Just write tangent as sine over cosine. So that would be sine of alpha plus beta over cosine of alpha plus beta. And now let's see, let's use the formula for each of these. So sine of alpha plus beta, that would be sine of alpha cosine of beta plus cosine of alpha sine of beta. And then the cosine of alpha plus beta, that's cos minus, remember it changes the sign. And then we have sine. Okay, so now, instead of leaving it like this, we're gonna clean this up a little bit, okay? So I'm gonna play some tricks, actually not some tricks, just one trick. I'm going to divide top and bottom by cosine of alpha, cosine of beta. In other words, I'm gonna divide top and bottom by this guy, all right? So look like this, so we have sine of alpha, cosine of beta, and dividing this by cosine of alpha, cosine of beta. And then we have plus cosine of alpha, sine of beta. And the reason why we are doing this, it will be apparent in a second. Notice that we have some nice cancellations, and then whatever is left, it will turn into something nice. Over, and then in the bottom we have cosine of alpha, cosine of beta, minus sine of alpha, sine of beta, and then we have to divide by this as well. Okay, so we divide top and bottom by cosine of alpha times cosine of beta, and the reason why we did that is apparent now. Notice that in here, the cosine of betas cancel out. So what are we left with? In the first term on top, we have sine of alpha over cosine of beta. What is that equal to for the first term? What's sine over cosine? It's equal to tangent. So we have tangent of alpha. Now in the second term, what happens? Notice that the sine of betas now are the ones that cancel out. And then what do we have? And the cosines also, they cancel each other. I think I mistyped something. The sine cos, cosine. I feel like I wrote something wrong. Cos, cosine, sine. Oh. Okay, so it's cosine of alpha, cosine of beta, what I'm dividing by. So this is cosine of beta. Should complain. You see that? I had a sine of beta, and it's cosine of beta. Okay, that's what I'm dividing by every single term. It's cosine of alpha, cosine of beta. Okay, so the cosine of alphas, they are the ones who cancel. So what are we left with? So plus, then we get sine of beta over cosine of beta. So again, we have sine over cosine. So this time we get tangent of beta, and then divided by, and what happens in the bottom? Here everything cancels out. So we get a 1, and then minus, and then in the last term, what happens? Let's see. Okay, nothing cancels, but we can rewrite that nicely, right? Sine of alpha over cosine of alpha, that's just tangent of alpha. Sine of beta over cosine of beta, that's just tangent of beta. Okay, so tangent of alpha times tangent of beta. In other words, the tangent of alpha plus beta equals tangent of alpha plus tangent of beta over 1 minus tangent of alpha times tangent of beta. And that's a nice little formula in terms of tangents. Questions? We're going to see an application of this pretty soon. Questions? Okay, now I don't want to do this calculation again, so let us reuse what we just did. In this calculation that we just did, imagine that instead of plus, we had a minus. Tangent of alpha minus beta. What will happen then? We will have a minus here and a minus here. So we will have sine of alpha minus beta divided by cosine of alpha minus beta. Everybody following now? So follow the green signs now. Okay? Just want to get a formula for tangent of alpha minus beta. Okay? I'm gonna just reuse what we have done. Are you following what I'm doing so far? Okay, so then on top, then what do we get? So remember, when you do sine of alpha minus beta, that respects the symbol. So if it's minus, then it will still be minus on top. But the cosine, it flips it. So instead of being a minus, then it's going to turn it into a plus. Okay? And so that means that we have a minus here, we have a plus here, meaning that we're going to have a minus here, and we'll have a plus here. And that's your formula for tangent of alpha minus beta. So here I wrote two formulas, one with plus, just use the symbol on top. If you have a minus, alpha minus beta, then you use the symbol in the bottom. Tangent of alpha minus tangent of beta over 1 plus tangent of alpha times tangent of beta. You okay with this? Okay, good. You know, same way that you put your plus or minus in the quadratic formula just to have the whole thing combined together in a nice little expression. That's what I'm doing here. Okay, so let us actually see an application. Let us see how we can, let us explore this tangent business further. There is something nice about tangent, okay, when you look at the tangent of an angle. So let's do a couple of applications in which we're going to take advantage of that identity that we have there. So we're going to do this example, and then we're going to do a little word problem, okay, and just to solve this little problem. Okay, but let's focus on this one first. Okay, suppose that you have two lines, so let L1 and L2 denote two non-vertical intersecting lines. So these are two lines that are not vertical, okay, so they don't make a 90-degree angle with the x-axis, and they cross some point, okay, two non-vertical lines that intersect, and let's suppose that theta is the acute angle between them. So, you know, you have two lines, they're not vertical lines, so you can just, and just randomly writing the lines, L1, L2, and then, as you know, when two lines intersect, then there are two angles that are created. There are four, but they come in pairs because they are equal of each other, right? So there are two angles mainly that are created. We have this little angle right here, the green, and then we have this angle here. If you know one angle, then you know the rest, right? Because the green and the black, they are supplementary angles. They are up to 180. And then the other two, you can get it by, you know, they are vertical angles. So this is also the green because they share the same vertex. And then this is also the black. So you can figure out those. So this question is talking about this one, okay? Figuring out theta. Once you find theta, then you can find everybody else. So this is about how you find the angle of intersection between two lines, really. That's what this question is about. If you know two lines, you know that intersect, how do you figure out the angle at which they are crossing? Okay? And to do this, then what we need to show is the following. So you have two lines that they intersect at a point. Let theta be the acute angle between them. Show that the tangent of theta actually can be found by looking at the slopes of the lines. Okay? So here M1, M2 are the slope of L1 and L2 respectively. And then the question says to show that tangent of theta can be calculated by doing M2 minus M1 over 1 plus M1 times M2. Okay, so let's try to prove this. All right, so again, notice that once we do this problem, this will give you a way of figuring out angles between lines, okay? Because if you can find, if you have the two lines, that means you have the equation, so you have their slopes. This formula will allow you to come up with the tangent of the angle of intersection, and then you can find the angle by just doing inverse tangent, right? Because theta is acute. Notice that theta is acute, so that means that it's in quadrant 1. So once you know this formula, then this will imply that theta can be calculated by doing inverse tangent of this number. You know, and this is a pretty good application, because you know, we always want to find, whenever two things are crossing, at what angle do they cross. So this will tell you how to find intersection, the angle between two lines. And when you get to calculus 3, for example, you're gonna find another formula that will tell you how to find the angle between two vectors. And it's a similar thing. You can actually get the formula from here, because when you have a vector, you can think of that vector as being, you know, a line. It's just a piece of that line, and then you have another vector, right? And if you want to find the angle in between, you can consider that second vector as just being another line, and you're just looking for the same angle that we're looking for right now. So we have the situation in Cal 3, and then also then you have more general cases, like how about the angle between two planes? This is two lines intersecting. What if two planes intersect? At what angle? How do you figure out the angle of that? But that's a story for calculus 3. All right, so back here, let's try to use the little trick that we have discussed to try to come up with this question. In other words, I'm giving you the formula already. We just have to verify. So this is really a proof of what we're doing now. Okay, so let us do a picture of the situation. Remember, we should always draw some pictures that hopefully will, you know, enlighten what's going on. All right, so we have two lines, and nothing. All we know is that they cannot be vertical lines, and they are not. And they cross at some point. Okay, and so well, I guess before I draw a picture, before I answer the question, let me tell you something more. Why is it that we can say something about the tangent of an angle and the slopes? Why not something else? And here is a little remark, which is actually a big remark, if you want. So imagine that you have a line, just any line. For the sake of argument, just gonna draw, you know, a line with positive slope. But it doesn't have to be positive; it could be negative as well. Okay, so you have a line L, and this line has equation mx plus b. Okay, so this is your line L. Now, every time that you have a line, you know, it always makes an angle with respect to the x-axis. So the angle, let's focus on the angle that it makes with the positive x-axis. Okay, and now let's pick a point on the line. Let's pick a point here on the line. Let's call it A, B. So whenever you do this, just you can pick any point on the line. You can calculate the slope of this line L, because as you know, if we drop here, this is gonna be a perpendicular, right? And the slope of the line is rise over run. So just focus on this point right here, the x-intercept of the line, and then the point that we chose. So this is the run, let's call it delta x, and this is the rise, let's call it delta y. So from here it follows that the slope of the line can be calculated as the rise over run. Everybody okay with this? Do you see this? Okay, now let us focus on, let's go back to trick now. Notice that whenever you do that, there is actually a triangle that we're using to do a rise over run, okay? And that is a right triangle. And in that triangle, we have theta, which is the angle that the line makes with the positive x-axis. And notice that delta y is just the opposite side, and delta x is just the adjacent side. So really what we have here is opposite over adjacent. What trigonometric function comes to mind whenever we have opposite over adjacent? It's tangent. So this is just tangent of theta. Okay? So this right here is a very important relationship. So if you want to figure out what's the angle that a line makes with the x-axis, when you draw a line, it always makes an angle with the x-axis, unless it's a horizontal line, which is parallel to x-axis, so the angle, if you want, is 0, or vertical line, the angle is 90 degrees. But otherwise, any line, now we have a relationship. The angle that it makes with the x-axis is always the tangent. So the tangent of that angle is always the slope of the line. So notice that if the angle is acute, if the angle is less than 90 degrees, then that means the line is going up. So, and as you know, tangent of theta is positive. So positive slope is another way of saying why positive slope means going up. And if you make an angle that's more than 90 degrees, so something like this, right? This is an angle that is in quadrant 2, then the tangent of this angle is negative because it's in quadrant 2. So the slope is negative. And that's why when you have a negative slope, the line is going down. Now you can analyze it from this point of view, okay? So this allows you to find angles, the angle of a line, by just looking at the slope. The slope is the tangent of the angle. Questions? Questions on this? All right. So then, that's why it makes sense to say, well, if you have two angles, if you have two lines, you know that each line has a slope, and the slope of each line has to do with the tangent of a certain angle. Now, if you have these two lines intersecting, we would like to figure out a relationship between this angle of intersection and the slope of these lines. And it should not come as a surprise that we're going to be using tangents to help us out here because of the formula that we just saw for the tangent. Okay, so that will motivate the picture that I will do, okay? All right, so solution. So now we solve the problem. So that's a very important fact, what we wrote there, that the slope of a line is given by the tangent of the angle that it makes with the x-axis, okay? With the positive direction of the x-axis. All right, so let's see. Back to our problem. We have two lines. So we have two lines. Let's draw a big picture. That way we can see everything that's going on. So let's call it L1, and just draw it like this. Okay, let's say that this line here is L1, and then so let's say, without loss of generality, let's say that the slope of L1 is bigger than the slope of L2. I'm also gonna do the picture for positive slopes, okay? But it doesn't have to be; it could be negative slopes. So let's say this is L1, and then let's say that we have here the line L2. All right, so several things happening here. So let's see. Here we have the angle alpha, and then here we have the angle beta, which is the angle that makes L2 with the x-axis. And then another construction. Here is a point of intersection, and we have here the angle that we are interested in. This is the theta that we're looking for, the angle of intersection, the acute one. All right, so let's do the following. I'm gonna draw here a horizontal line. This is a line that's parallel to the x-axis, okay? Because I want to bring alpha and beta into the picture where theta is. So let's see if you remember this. We discussed this way earlier at the beginning when we started talking about trigonometry. And I don't even remember if we discussed this. I think no, this is clear geometry. We haven't done clear geometry. This is something that you do back in high school. So in high school, you learn how to talk about angles between parallel lines, okay? So in particular, this line that I just drew, the dotted line, is parallel to the x-axis, okay? So we have this picture, and then here we have the line L1, okay? So we have that down here is alpha. So let's see, is that, okay, before, no, I don't want to look at L1. Yes, let's look at L1. Is L1, we have that this angle here is alpha. Can anybody tell me what is this angle? What's the measure of this angle up here? This is something that you learned back in high school. Can you tell me what is this? This one. The one that I did in black. That's alpha as well. Very good. So these are called corresponding angles. Okay. So remember that when you have parallel lines and then a transverse line, this type of angles are called correspondings, the ones that are on the same side of the transverse of the secant line, and one is inside, another one is outside the parallel lines. They measure the same. Okay. So in back to our picture, when we put this picture together, that means that this one up here is alpha as well. Everybody okay with this so far? Because that's the corresponding one to the alpha that we have down in the x-axis. You okay with this? All right, perfect. So let me keep these. And then in a similar way, let's do the same thing. Here we have our x-axis. Then here we have our dotted line. But now let's focus on the line L2. So when we have the line L2, down here we have beta. How about this angle up here? Who can tell me what is this angle up here? What's this angle? On top is also beta, right? So same thing that we did as before. So this guy is going to be beta because they are corresponding. So that means I have here, this little angle here is beta. Okay, perfect. Now with this picture, we can begin working. So questions about the picture before I start writing stuff down. Okay, all right, so now let's focus, let's focus right here. This is what we want to focus our attention on right now. Okay, so in that picture, we have three angles. Can anybody tell me what relationship do we have between these three angles? Let's see. What relationship do you observe between the three angles, theta, beta, and alpha? Are you looking at that picture? They are the sum of each other. Okay, that's a little bit ambiguous. What do you mean? Say more specifically. Which one is the sum of what?
So beta would be the sum of beta plus alpha. So that's what I mean.
Okay, so you mean, okay, you're breaking up a lot. Okay, well, I think I understood what you told me. So basically, it's that alpha equals theta plus beta. Does everybody see this? If we put theta and beta together, we get alpha. Well, notice that theta is very tiny. I mean, theta is smaller than alpha. Just look at the picture. It would be alpha equals theta plus beta. Do you see that? So does everybody see this? If you put theta, the green angle, and beta, the red angle, put them together, you get the blue angle, alpha. So from the picture, we see that alpha, which is the big angle, equals theta plus beta. Yeah, I see. Yeah, that's fine. It's just that, this is coming from the Greeks. Trigonometry comes from the Greeks, and that's why we just we stick to Greek letters because, well, in honor to their legacy, I guess. Okay, so questions. Do you understand this? That alpha is theta plus beta? Does everybody see this relationship? Okay, now of course we are interested in theta, right? Because the question is theta is the acute angle, and then the question is about what can we say about tangent of theta. So we immediately from here write, okay, so if alpha is theta plus beta, then from here it follows that theta is gonna be, so what is it? Alpha minus beta. So now, of course, we want to know what's tangent of theta, right? That's the formula we're trying to verify. So taking tangent on both sides, we get that tangent of theta equals tangent of alpha minus beta. And now we can go ahead and use our beautiful formula. What do we know about tangent of alpha minus beta? This was the formula we just proved. So tangent of alpha minus beta is tangent of alpha minus tangent of beta over 1 plus tangent of alpha times tangent of beta. So this is tangent of alpha minus tangent of beta over 1 plus. So you keep the sign on top because remember, tangent is sine over cosine. Sine respects whatever symbol you have, cosine flips it. So that's why the minus stays on top, but then the bottom we need to flip it. 1 plus tangent of alpha times tangent of beta. Okay? But then, according to the observation that we did earlier, what do we know about tangent of alpha? What's tangent of alpha equal to? So remember, alpha is the angle that the line L1 makes with the x-axis. So tangent of alpha is just the slope of the first line. Tangent of beta is just the slope of the second line. And then we already have that. So M1 times M2. And we get the desired formula. But the tangent of an angle between two lines is given by the difference of the slopes divided by 1 plus the product of the slopes. Okay, questions? All right, so that's one little application that we can do. Let's see, let me move these things a little bit to the right. All right, so that was that. Now let's take a look at the next problem. So example 2. For a climbing wall, a guide wire R, so we even provide the picture, so it's easier to understand what's going on. The guide wire R is attached 47 feet high on a vertical pole, so we can see that in the picture. Added support is provided by another guide wire S 40 feet above the ground. That's also noted in the picture on the same pole. Okay, good. If the wires are attached to the ground 50 feet from the pole, that's also in the picture, find the angle alpha in degrees between the wires. In other words, there is that little angle alpha that we have there between the wires. The question says to find it. Does anybody understand the question? Do you guys understand the question? Okay, so now we want to find alpha. How can we do this? Well, notice that we have the two wires R and S, and they actually, each of them, they define two triangles, right? Two right triangles. So R has the angle beta, has the triangle with angle beta, that's good. So S will give us another right triangle, but we're not given the angle in the picture, so let's put it. Let's call it theta, okay? So that means that now with this relationship, we can see that alpha can be obtained by doing beta minus theta. So from here it follows that, so solution. So the alpha that we're looking for equals beta minus theta, where theta is as we just draw it in the picture. So then the tangent of alpha, so if you want to figure out alpha, then one technique is, first of all, notice that alpha is in quadrant 1. Looking at the picture. And so if we want to find alpha, we can first calculate the tangent of alpha, if we can, and then we do inverse tangent. Everybody understand this? We're going to do tangent so that then we can do inverse tangent. Do you follow this? Okay, what I'm saying is that to come up with alpha, because I want to use the two right triangles. And notice that in the right triangles that we have opposite and adjacent. So that means we're going to be working with tangents, formulas for tangent of beta and theta. Okay. So what we're going to do is we're going to figure out the tangent of alpha, and once we get that, then we're going to use inverse tangent to come up with the angle. Okay. So in other words, if alpha is beta minus theta, then tangent of alpha is going to be tangent of beta minus theta. Okay, so let's first find tangent of alpha, and once we know this, then we can come up with alpha by doing inverse tangent. All right, so tangent of alpha is tangent of beta minus theta. I'm gonna use the formula. So as tangent of beta minus tangent of theta over 1 plus tangent of beta times tangent of theta. This is using the formula that we saw earlier. Okay, good. So now that we have this, then we can just put in the values, right? By the way, you could also do this problem another way. You could consider the two wires S and R as being lines, right? And notice that alpha is actually the angle of intersection between these two lines. So you would just, if you want to use the formula from the previous exercise, you will need to figure out the equation of the two lines first, which you can do it, or just the slopes, which you can do it very easily by looking at this, the relationship, the rise over wrong of the slope of this line, and then you will get exactly what we're about to write. Okay, so let's see, tangent of beta. What's the tangent of beta? That's opposite over adjacent, so that would be 47 over 50. Looking at the big triangle. Now looking at the small triangle, for tangent of theta, we get opposite over adjacent, so that's 40 over 50. Divided by 1 plus 47 over 50 times 40 over 50. Okay, questions on this? All right, so now let's just calculate this, okay? I'm just gonna simplify. So I'm gonna multiply top and bottom by, let's say, 2500 by 50 squared, just to get rid of those little fractions. So we get the tangent of alpha is gonna be 47 times 50 minus 40 times 50 divided by 2500 plus 47 times 40. So let's see, what is this? So 47 times 50, that's 2,350. Then we need to do minus 2,000, right? So that's 350 on top. And then in the bottom, we have 47 times 40, and then plus 2,500. So we have a 4,380. We could do a little bit better than this. We can simplify, so the zeros cancel out. So we got 35 over 438. Okay, good. So now this is tangent of alpha. Now remember, if we want to figure out alpha, what do we need to do? We take inverse tangent. And we know that alpha is in quadrant 1, so we can just do inverse tangent, and we know that the calculator is going to give us exactly what the angle is, because the range of inverse tangent is quadrant 1 and quadrant 4. But in this case, because alpha is in quadrant 1, we're going to get the actual value, because 35 over 438 is positive. Anyways, now we just use the calculator. Okay, make sure that is in degrees. So make sure that you use degrees mode, because notice that the answer says find the angle in degrees. Okay, find the angle alpha in degrees right here. So let's see, go ahead and figure it out. Tell me what you get. Make sure that you understand how to do this. Or hopefully you already calculated that. So I just did it with my calculator, so you should get 4.57 degrees. Very good. Very good, Maria. So that little angle alpha in the picture is 4.57, about 4.57. Okay, degrees. Questions? Questions of this application? Okay, perfect. So again, you just need to be aware of all of those formulas and identities that you just saw, okay? And as you use them in your career, I mean, you're gonna be engineers, most of you, many of you, and you're gonna be using these things left and right, okay? So at some point, you will just remember these things. But right now, I just want you to be aware these formulas are out there, and so that you can find them whenever you need them. So you should write, in a little piece of paper these formulas down, so you have them organized, all the identities that we have figured out so far. Okay, so that was for the sum and difference formulas, and that's what happened in section 7.2.